oscillation. As you can see, the output lags 180 degrees behind the input. The MOT here is the input into the system. There's CT output. MOT is equal to A sine 2 pi ft. A being amplitude, AR of T, and F being frequency. And the output then is equal to the amplitude ratio times the amplitude times sine 2 pi frequency times time plus the phase shift. RT here is the input into the system, EFT is the error, or RT is the inputs, EFT is the error, FT is then the input into the system. Here's MOT equals C. Sorry, that there's supposed to be 180. And EFT is then equal to the input minus the output.
And to find what happens at the output when the phase angle reaches minus 180, as you can see, the formula for the output is amplitude ratio times A sine 2 pi ft minus 180 degrees. Going back to Cal 2, or whichever math it was, sine of two angles subtracted from each other is sine A cosine B minus cosine A sine B. So apply that to the output formula, and you have sine 2 frequency times time minus 180 equals sine 2 pi ft times the cosine of minus 180 degrees plus the cosine of 2 pi ft times the sine of minus 180 with the cosine of minus 180 degrees being 1, and of course the sine at minus 180 degrees being 0. That shortens the whole situation drastically to where we'll have that sine of 2ft minus 180 degrees being sine 2ft times minus 1 plus cosine 2 pi ft times 0. So the output that we get total is minus the amplitude ratio times A, which is your magnitude, times sine 2 pi, F being the frequency, times T being whatever time it is. Therefore, well, as a result of this, as I said before, the output is minus AR times A times sine 2 pi ft, and M sub T, the input that goes into the system, being A sine 2 pi ft, which as we said before, that when the output lags the input by minus 180 degrees, they mirror each other. The two sine waves mirror each other, the exact opposite.
Error of T, which if you go back to the standard block diagram, which is not shown here, the error equals the input minus the output to get the error, which then goes in KC, where R of T equals 0 and C of T at 180 degrees equals, as before, AR times A sine 2 pi F. Okay. Oh, sorry. Oh, that's a negative. AR A sine 2 pi frequency times time. So where we have, plugging it in, the RT equals 0, CFT equal AR, EFT equals 0 minus a negative AR times A sine of 2 pi frequency times time. So where we have EFT equals a positive AR times A sine of 2 pi function of time. So now, with all the equations that we have accumulated so far, we have the manipulated variable-like function of time equals amplitude times sine of 2 pi frequency our output is negative amplitude ratio times amplitude times sine of 2 pi f of t. So, and with our newest addition to the list, we have error function of time equals amplitude ratio times amplitude times sine equals 2 pi function of time. We should just listed it. So now with our error function, we have a manipulating variable as an input function from the loop function. Diagram. We have Kc times error t because the error goes into the Kc block and comes out as the manipulated function, which then goes into the system, which then comes out as error of t. Well, with that in mind, our E of t equals AR times A times sine of 2 pi f t. And so with all these plugged in, we have M of t equals Kc AR A sine of 2 pi f t. But as stated earlier, M of t was supposed to equal A sine 2 pi f t. So if we set these equal to each other, with all the accumulated, we have M of t equals that, and also M of t equals that. So this being the initial input to the system, and this is being the output for the controller once it goes back into the system afterwards. For case finding the amplitude ratio, we have M of t equals M of t, and since they both have A amplitude times sine 2 pi f t, and we just divide both by that, so we cross out the A sine, and then we have the A sine, so we have 1 equals Kc AR, and to solve for AR we divide by Kc, so we have 1 over Kc equals AR. And if this is a KCU, this is supposed to be some kind of proof. This is actually works in according to my sources. I know it's a little confusing, but if you find out the KCU of your system, it works because somehow it would keep it oscillatory at all points, and this is going to be like a recording on parts of the presentation, I can tell.
So
Okay.
basically, what does this all mean? Well, going back to the beginning, where we had the graph, with the formula that we found for the output, say, ends up being right around here. What the system reads as the error is exactly what happens on opposite end. So as a result, the system is going to send a response to the system the exact opposite of what the output is, because at KCU the output lags the input by minus 180 degrees. So as I said before, the output and the input basically mirror each other. So whatever you get for the output, the system is going to see that, recognize it as complete error in the complete opposite direction, and send as a result the input in, well, it's going to send this as an input, which will drag your output even more. As I said, they'll keep mirroring each other. The amplitude ratio should equal 1 at this particular function, so what happens is they'll keep oscillating and they will never die down. If you manage to bring the Kc value higher than that, then the system becomes unstable. Lower than that, and you end up having a steady state value. That being said, any questions?
Take a survey of the other, of various teams.
We got some of the data. Fine. What we asked for the sinus cell responses, we didn't get sinus cell responses. For Purple's team, do you want to break this on the board, or you want me to?
solar system, for my region, I managed to get a KC value of 26.1, 26, and the frequency associated with that was around 0.714 cycles per second. So, with that being said, if you plug it into all the formulas, basically the output and the input will be exact opposites of each other.
Clear up something that amplitude ratio isn't always 1 at the ultimate frequency, because you can have a sine wave with, like, you know, because you could have, like, you know how, like, the input isn't the same as the output. Like, input could be, you know, 40% and oscillate, like, you know, like 10%, but like the output could be like 100, you know, gallons per minute of water, or just some random thing like that. So the amplitude ratio can actually be like, you know, anything you really like. Like it could be like really high, really low. It could be